the Quinn's status report, I would say. Being absolute professionals, we will give a completely unrehearsed, sliced together presentation. Let's hope we stay in time. And as you can see, we are a very happy group of people here. We had a very good time. We will check the photo after and splice it in after the fact. So for the last 3 weeks, we've been throwing out a lot of words. We have the best words. And we learned a lot. I think it was a steep learning curve for most people in the project because before, I think most of us didn't really do anything in this area directly. But it was quite interesting. And we actually, over the time, we really converged on a core idea that we already presented in between, but as a brief recap. So we wanted to work with NP-hard problems, so a bit out of the normal scope of neuromorphic computing stuff. And these problems are typically formalized in like very math-heavy context, and so we want to map them into a specific form that can run well on neuromorphic hardware. And this form is called QUBO, and there's basically two versions. There's QUBO, which is the upper one, which is quadratic unconstrained binary optimization. So we're trying to minimize some function over binary vectors. The other formulation here is the Ising model formulation, and they are equivalent. And so this is a long-studied type of problems that people are trying to solve. And this, I already showed this before, so it's actually a hard problem. So you will not get, with today's ChatGPT, you will not get an answer for this, but with tomorrow's, you might get one, and we will get to this in a moment. So the idea here was always to take these matrices, to map them into some models that can run on neuromorphic hardware, ideally just leaky integrated fire neurons, even though they are maybe not the optimal way to do this, and then to run this on neuromorphic hardware. And then we get spike vectors back, and these spike vectors we can then translate back into the QUBO form, where we then have binary vectors of these variables, and from there we can finally go back to the original problem solution. And since this whole chain is a little bit complicated, and also like we don't want to have to reinvent the wheel for every different problem, the idea was to basically simplify this process and merge all of these different pieces into one package. Yes?
What's QO?
Quadratic unconstrained binary optimization.
You just said that.
Yes. So quadratic because it's a quadratic matrix equation, and the unconstrained actually I'm still confused about, to be honest.
I can explain that.
Okay, I will explain it. So this problem, it looks like a simple thing, but it falls apart into many different subproblems. So for each of the different type of optimization problems we want to solve, we basically need a different front end to allow people to specify the problem and then map it into the QUBO form, but then also from the QUBO form to different models that we want to run. And we will now go through the different groups that were working on different subproblems here, and they will basically present what they've been doing for the last week. And I think the first one to start is Adil.
I'll get the boring stuff out of the way. Okay, so this is a cartoon that I Googled about 5 seconds ago, and I put that in. So basically, as Jonas said, QUBO stands for quadratic unconstrained binary optimization. And what it means is we're trying to phrase our problems in a very general mathematical framework where we try to only work with binary variables. So all of these, for example, x, these are binary variables. And we also only work in sort of quadratic interactions and linear interactions here. This is linear because if this is a binary variable, we get the product, and that's linear. So what we try to do is we're trying to phrase every problem in this framework and trying to phrase it so that once this equation is minimized, we reach a solution. Now, the question is, why have we restricted ourselves just to this? Why have we said we only want to work with binary variables, quadratic interactions, and linear interactions? And that's really the core of this whole project, and we'll discuss that further. Right, so it's almost like QUBO and neuromorphic hardware were meant for each other. So for example, when we're working with binary variables here, you can think of the binary variable being mapped to a neuron, mapped to a binary neuron, or even a spiking neuron. So there's a one-to-one correspondence there that's very natural. In the same way, we have the quadratic terms here. You can think of this as being the synaptic weights between neurons, and the linear ones being biases for the neurons. So there's a very natural correspondence between these two, right? So in general, what we're saying is that the Q matrix of this form actually describes a network. It describes a neural network that we can follow. It's a recipe. We can construct a neural network where each variable maps to at least a neuron, and the synaptic weights are given by the coefficients of our equation. And the beautiful thing is that if you construct the network the Q matrix is telling you to do, and you let it, for example, relax, or you let the dynamics happen, the network will settle in a state that actually solves our problem, that actually minimizes this function. Now, that's not very obvious why that happens, but you can think of this as an energy function, and there's an equivalence between systems in physics and, of course, this form. And this is kind of like the energy of your neural network, and it always tries to minimize that. So if you're able to construct the Q matrix and write a problem in this form and build a neural network, you are guaranteed at least to find some local minima that's going to try to reach the solution. So that's why we're working in this form, because it maps naturally to neuromorphic hardware. Right, so let me now give you an example of how you would go about to kind of phrase or construct a problem, right? So this is a very simple problem that we showed in the demo as well. So we have a set of boxes with some volume, and we want to pack that into a truck, for example, that has a height restriction, and each box has a height, and we are wondering how we can maximize the volume that we are packing without exceeding the height constraint, right? So now, very naturally, a box is either in the truck or not, so that's a binary decision. We can map that to a neuron. And then once we go through the problem and we turn the handle, we realize that the synaptic strengths will be determined by the actual volume of the boxes, the other constraints. So this is how you are building that network. So mathematically, we're four detail here that we're trying to maximize the volume with the constraint that the height of each box doesn't, the sum of the heights doesn't exceed the constraint. Now, the reason I've got that there is it also gives some insight into the network. So for example, here, you have an inequality. What that says is that these neurons have a lot of freedom. They can choose many states that will all equally respect this constraint. So what ends up happening is that a constraint such as this gets mapped to additional neurons, right? So, and terms like these lead to interaction, lead to quadratic interactions once you go through the maths. So this is how you would go about constructing the Q matrix. This would, or the objective function. This would be part of the objective function, then this would be part of the objective function. So you construct that whole equation. And inequalities would generally lead to more neurons and more interactions that try to enforce these requirements. So let me now show you a quick animation of how this is. We did that. So this is solving this problem with 18 neurons. So we needed 10 neurons for the actual boxes and 4 for the constraint. And you can see that eventually it reaches the final. I'll play that once more. So you can see that this is the actual coupling that's determined by the Q matrix. So the thicker the color, the thicker the line, the bigger the weight. And you can see that these 4 auxiliary neurons are actually just enforcing that height constraint. And then these 10 represent each box. And they fire and they go through a solution. And eventually, we get to, if I can pause it right at the, oh, I guess I can't. Come on.
Well, we saw it.
Yeah, we saw it.
Yeah, great.
Yeah.
Okay, perfect. So now it's, yeah.
Yes.
Yeah.
Yeah, so this is the work which was done by Zili and Zihal, who are online. I'm just presenting on behalf of them. So we also ran different algorithms and architectures on this max-cut benchmarks. Max-cut is generally considered, yes.
Talk louder, please.
Yeah, okay. So max-cut is generally considered one of the simplest benchmarks, but it tells you how good some of these optimization algorithms are going to work. So for example, like yesterday, IBM Group, they published a paper in Nature talking about like how their quantum annealing algorithm performs on the max-cut benchmark. Interestingly, what they showed is that they get a speed up, but they don't improve the accuracy of the solution. Okay. So what we are showing here is that so for this specific benchmark, the best possible result is 3065. With simulated annealing, which is the out-of-the-box algorithm, we get to about 3058. What the speaker yesterday, Brad Imon, he had presented an algorithm. We ran that benchmark quickly. Doesn't even come close to that, what the state of the art is. Now, of course, there are some hyperparameter tuning that needs to be done. And then there are these different type of SNN architectures. So we tried off bifurcation, there are some growth transform neurons, and then combining SNN and annealing gets you pretty close to the number, but we are still there, not there yet. Okay. And then once we get to the resonate and fire neuron and combining these two, then we start getting close to the benchmark. So, so the moral of the story there is that, of course, things can be done, can be mapped onto a spiking neural architecture, but there are some bells and whistles that we have to take care of before we can efficiently do that. Okay, and noise plays a very important role, and annealing schedule plays a very important role. So those are some of the take-home messages from this study that we found. Next slide.
Can you describe what the benchmark means? Like, how big is the gap between 3064 and 3058?
So 3064, 36, these are the number of cuts. So the max cut problem is that you have to partition a graph into, so you have to partition the nodes of the graph into two sets, such that the number of interconnections between those two sets are as maximal as possible. So for this benchmark, 3065 is the maximum number of cuts that you can achieve. Okay? And that's also, we don't know that 3065 is the best number. That's to date, that's the number that has been reported. So if we can beat that by one.
3065, okay.
3065.
Okay, so we have nice to know that. Put another line there, so we have the gold standard.
Yeah. So even if we get to 3066, you have already beaten the world record there. So again, these tasks are more related with discovery. You're trying to find new solutions to an existing problem.
15 minutes.
Yes, okay. Is Chad here? No. So I will just talk about what. So this was a problem that Christian, when he was here first week, he told us that. No, he told us that okay, there is this industrial problem which we refer to as the German steel problem here, and it had this. It is based on some scheduling procedure. What he mentioned is that they have a bunch of mathematicians that have been working on this for a long time, trying to get the optimized schedule, but this problem has to be solved in real time. That's their biggest constraint. So Chad, he went through all this maths. I'm not going to go through this detail, and you have to go through all this math to get to that cubo matrix. Okay? So one of the objectives of this work group is to kind of formalize this process. So you don't have to go through this math. You just describe the problem, and then the compiler takes care of it and gives you the cubo matrix. Okay? So with that, I will give the forum to Mendel.
Yeah. So yeah, Nick and I took this then the next step of this process, which is taking this Q matrix and then mapping it to SNNs, and in this case, running it on Spinnaker. So as Adil and Shantanu explained, we have this matrix, and this matrix has values that correspond to the synaptic weights between neurons. So we created that in Spinnaker. We just lay out the network definition, taking this matrix, defining the connections, and we just simulate it. But to simulate it, we, as Adil also mentioned, we need to add some noise. We need to perturb the system to get the dynamics going. So we tried different methods to do so. So we tried injecting random spike trains into random neurons. We tried injecting noise on membrane potentials randomly at each time step. We tried also introducing random delays in the network. So when a spike comes in, it will be delayed by X time steps randomly. And also we randomized the input weights. And to read out the outputs of this process, we can either read the spikes or the membrane potentials. So here you see an example of reading out the membrane potentials of 10 neurons. And we basically classify them in two groups. So one group is just here, these are spiking neurons. We set the threshold to 0. So these are just called spiking, and here we have negative neurons. And then this way you can classify them into two groups. And this will give us like this X vector that we will then plug into the equation that I will show them. This will give us the number of cuts. So here we see that for the 5-node max cut graph, we reach the maximum number of cuts, which is 5 very quickly. Now we wanted to extend that to a bigger graph. Do you want to?
Yeah, so I mean, the benchmark that we talked about before is a graph with 800 nodes. There we tried to do the same thing. And so here in this case, we were reading out, so this is input spike trains. This is the spike activity of the cubo matrix. And here you see the number of cuts over time. So we try to find a configuration that would maximize this number of cuts here. So we would just look at those neurons and we would see either they spike or they don't spike. So they're either in the one side of the graph or the other. And yeah, so we tried different things as Mahmoud was explaining. And so far we didn't reach the state of the art. I think we ended up at like 2,970 or 80 or something like this. You can see that here. And I guess here, this is really, yeah, this is where we're working on. Like, how can we optimize this? Like the big premise is this is super fast. So if you run this thing in annealing, it will take seconds to minutes, where this thing is running in like 200 milliseconds or something like this. So if we can achieve like a state-of-the-art solution with this approach, this would be really cool, because then we could scale it up and have really fast solutions to something that takes usually very, very long.
Yeah, so maybe the last point here is some hardware limitations we faced when we were running the bigger graph on Spinnaker. So one thing is that we cannot run, because this has like 1,600 neurons that we were simulating on Spinnaker with a lot of connections. So we have some memory constraints. So we were not able to run the simulation for a super long time. And maybe this will give us better results in the future. We also have some weight precision problems. We can only use 5 bits for the weights right now on this, using this neuron model on Spinnaker, and also logging voltages. So you see here for the bigger problem where we had to read out spikes and not voltages, because then it gets too much for the memory if we keep logging all the voltages for all neurons for a very long time. So these are things that we can then probably consider with the bigger Spinnaker boards that are supposed to come next month.
Yeah, what's that line?
This line?
Yeah.
Number of cuts per time.
What's the number? We
got the best year was like 2,950.
All right. So this was a slightly different take on the project. So the hyperdimensional computing or vector symbolic architectures, at least in the context of neural networks, are hypothesizing that the computations that are happening in neural networks are manipulations of points in high-dimensional vector Hilbert spaces. This mathematically connects us to quantum probability, which is how this project sort of fits under this venue. And then the hope, and because we know that we can translate all of these operations into neural networks, so every box in this diagram you see on the slide can be mapped to a neural network architecture. The hope is that we could define a circuit that where for any QUBO problem, we can use the same circuit to solve it. So that's why this was of value. And if you go to the next slide, what we've found is that for small problems, we can get reasonable solutions, although as the dimensionality increases, we need progressively larger vector representations to get good performance. And what we're seeing here on the x-axis is the number of variables in the QUBO matrix, maximum of 20, and then the y-axis is a mean absolute error, but due to the distribution of how I randomly generated these matrices, a score of about 10 points is about a 5% error, at least by the time you get out to 20 matrices. So this work continues. The major obstacle is approximation errors and approximating the QUBO function, and we're continuing to push forward on that. Thanks.
All right.
So this is the demo from yesterday. So I don't know who made it up the mountains yesterday to watch the Northern Lights. I did. I didn't see them. So we developed here a tool that might help us. So we have here a window where we can ask a ChatGPT query, and basically you're probably not going to see it because it's a bit small. But basically, I ask, where in the US can I see the Northern Lights, and what's the best path between those locations? Let's see if this runs.
Is this traveling salesman problem?
It's a traveling salesman or salesperson problem, which is also an NPR problem that we solved with QUBO, and if the video doesn't run, then it's sad. Do you know if there is some? Are we online?
Yes.
Okay.
It's the Wi-Fi. Just blame the Wi-Fi.
All right.
When did you upload the video? Just now?
No. Yesterday.
It was playing.
After my okay, there it goes. Here you go.
Yeah.
All right, so I'm typing the query that I want to see the Northern Lights, and it should calculate me the best path according to TSP, which is this problem. So now it fetches the coordinates. This is all ChatGPT. So we see, in our case, we're probably a bit too low. So this is in Alaska. Now it calculates the best path between those locations. And at some point it converges to a solution, which is this, and it prints out the output there. So that's the problem.
But if you were to ask ChatGPT to do it, you wouldn't be able to do it.
Not alone. I mean, this is what we said in the beginning. So ChatGPT calls our functions, and then we solve it and give it back to ChatGPT.
Yeah.
Or you could just look at those points and draw a loop, right?
Yes.
It's a hard problem, right?
Not for 7.9. Don't derail us. So, oh my wait, there was supposed to be a slide on higher spike, I think, or whatever. I mean, if not, I can also just quickly say there is it after, or where is it?
Yeah, it still needs to go down.
Okay, because it's supposed to be the last slide actually. Okay, then wait, when we were where is the slide?
That's 21.
20. Okay.
You can refresh it.
Yeah, whatever. Is it important? Should I just say like or can you just say in words like what you did? Because I don't want to go now to.
Okay, like we have like that's the other hardware. Can you refresh the slides?
Okay, can refresh this. Okay. Okay, 21. Yeah, I don't trust the connection here all that much. Okay. As I said, we are professionals here.
Technical.
Yeah. Okay.
Okay. So this is just the second hardware that has spike. Through which we used stochastic LIF here. So we achieved the score of 2900, which is still below the benchmark we have today. So in running this, we have a couple of things we learned in terms of neuron formation, there's oscillators, format, and also leakage. Leakage didn't improve the results in any way. So these were learned. So in terms of implementing the hardware, model on hardware, how it can be improved further, but then that's even in this model. So going further. All right. So this is just showing you how moving max-sats to Cubo. It's also a more difficult problem than max-cuts, and how we're able to just using clauses and literals, how number of first time satisfied gives you how much you need to solve the problem in real time. You just know how the combination is being done to form it on Cubo. So this gives you a picture of how just being able to use 3 variables and how we're able to map max-sat onto Cubo, and showing the map how we have each box showing you the intensity of how each matrix on Cubo shows you the intensity of what we get from max-sats to Cubo. Showing you how the intensity is, how this can show you from an algorithm platform, moving from like K-sat. So you can map from like K can be 5, 6, 7. So without to map onto a bit like maybe 2 or 3, we can go beyond that scale. So basically that's max-sat to Cubo for you. Thank you.
All right.
Can you hear me well? Yes?
Yes.
Yes, okay. The problem that I have analyzed here is the max-cut problem. That the solution for this type of problem, given a generic graph, consists in determining a cut of edges which allow to separate the vertices of the graph into 2 subsets. And the approach that I use here is to map the max-cut problem to the Ising problem model, and then build the corresponding spiking neural network. Next slide, please. Here is shown the pipeline that I used. Once the problem has been mapped in the Ising model, the network is implemented using GEN, a software simulator that allows to speed up the test in a very short time. And once the working prototype has been obtained, we then move on the hyperparameter optimization process that maximizes the solution rate with the NNI tools. And at this point, we will proceed to deploy the network on a Spinnaker 2 board, always performing an hyperparameter optimization to compensate the loss of the network capacity due to the quantization of weights. Next, please. And here, finally, here is shown some preliminary results. In the left-hand side, in the upper plot, there are shown the number of states of the network explored over time, while in the bottom, the objective function is shown. And here, as you can see, its value grows rapidly in a few milliseconds. And this means that the network is able to get close to the optimal solution as soon as the simulation has started. While in the right-hand side, instead, there is a video that shows the temporal evolution of the division of the vertices based on the color in a subset based on the cut and the activity of the network. So this is my project, and thank you for the attention.
It was a really nice project. I mean, we also had more people online. Not everyone could present now, but it was a real fun thing. Now the question is, how do we continue after the workshop? Because of course, like 3 weeks are not enough to finish everything. And so we have some homework. So we need to, for all of the different bits and pieces that you've seen, we will try to integrate all of them into really like this Python package that we started. So far, there's a skeleton of it on GitHub. And the first like simple stuff like conversion from integer linear programs to cuboform, for example. And we fill in all of these other parts. And ideally, someone will even document and test some of this. Of course. The second thing is we learned a lot during this process. And I think it's a quite interesting idea to go all of this way. I mean, we didn't come up with this idea, but I think we learned a lot about what works and what doesn't work. And so one idea was to really sit down and write a white paper where we explain this whole pipeline going from a problem via Cubo to the neuromorphic hardware in the end and getting some solution out. And of course, also like explain how you would do this with our Python code. We also had a couple of like more scientific questions that came up during the workshop where we didn't have time to really go into them. And I'm sure like in different subgroups, we will continue following up on them. And so for one idea, for example, that we discussed a bit is like what actually makes a problem suitable for neuromorphic hardware or not. And we can now look at these cubo matrices and we can see like, do they have structure that maps well to neuromorphic hardware? And if it doesn't, what are the hardware constraints that really limit us and things that we didn't think about before? Like, for example, the weight range. These matrices can have huge values. So how do you deal with that? And there are different strategies. So this is something that we would like to explore a bit more. Another question that is quite interesting is with the spiking neurons, we saw that we can get a solution, but maybe the neurons just fire too much because it's rate coding. Rate coding is not very efficient. So what is actually the minimum amount of energy you need? And intuitively, you should only need to communicate whenever one of these spins flip and nothing else. But what is the limit and how close can we get if we really try to do this in a more clever, sparse, event-based way? And of course, we saw one kind of real world problem and a lot of toy problems. So the question is, which other real world problems really can be mapped to this cubo form? And for which of these real world problems should we be using neuromorphic hardware in the future? So this is also something that we want to explore a bit more. And then the last one's maybe the most ambitious one, but we were in the process thinking a lot about what these neurons should look like to be efficient. And of course, one idea would be, why not just build it? Because if IBM can get a Nature paper for not advancing the state of the art, but just doing it a bit faster. If we can be faster than them, then we also deserve a Nature paper, right? So that's the logic here. Yeah, so we will think about it. We will definitely stay in touch. That's the plan. So the Slack was a very convenient tool. So please keep it alive. Yeah, that's it from our side, and hope to see many of you in many places.
Okay, so super glad we met here for the 3 weeks workshop for the open source neuromorphic hardware, software and hardware. Basically, we just don't want to rebuild the wheels all the time, just want to trade our work based on others' work. And we have a long list of contributors. If you want to read them, we have so many projects with this triangle relationship. We have dish brain simulator. We explore different learning mechanisms. We have diffusion model from event to frame. Like we have near representation for the continual learning, multimodal continual learning on A string, both with spec and Xylo. All the tape out, sparse spiking neural network, huge tape out. We have GPT assistant spiking neural network chip design and asynchronous chip design with all the open source tools. We also have some like LMUs based neural network, and then we have the fireworks data sets. So let's just start with the project. Simon, you done?
Yeah, it's me. All right. Good morning, everyone. We'll get started with the projects that you might have heard about, like on and on for the past week, with a bunch of presentation on it. I won't go on to what's the dish brain about. It's just like these neurons playing Pong. What we did, what Simon did mostly really the last weeks, was to train a bunch of agents to play Pong, to compare them. Yeah, there's a bunch of dish puns, by the way. Oh, the videos are not loading. That's great. Great. So, all right, demo time. This is what the dish brain looks like when it's playing Pong. That's like real biological neuron. This is terrible. Real biological neurons playing Pong. So what Simon did was reverse engineer the whole system, train a bunch of different agents, first showing that deep Q network, the classic reinforcement agents, were terrible at playing Pong. They just like kept messing, weren't learning anything. We reproduce all of the dish brain mechanism, train deep reinforcement spiking agents that were a bit better. Some of you might have played against them yesterday during demos. And then we managed to hack together yesterday a fully Avian spiking neural network that learns with the same kind of setting that the dish brain does, knowing the ball's position, spiking, trying to get reinforced, and getting better and better at playing the game. And I think nobody managed to beat that yesterday.
You go on the bottom right.
Weights on the bottom, spikes on the top. I'll play that one more time. Yeah. It's well, I don't know if the dish brain is a 3-layer, multi-layer perception, but this is what we model, right?
Dish brain is back.
Dish brain is background. Is Conrad on the meeting? No, we're not. And basically, yeah, we had all of these agents. We also had like the state-of-the-art if you want to buy a copy of the book, Simon will be signing after this kind of presentation. And yeah, so, what was really fun to do is that we also wired like a 2 kind of player system that people could play yesterday. Some of you who were at the demo, or if you want to swing by our laptops today, we can still try to give you a feel for it, like playing against different kind of agents, trying to see how the dish brain learns versus traditional reinforcement agents, and showing that like biological like computation really are the way to go when having to learn spatial-temporal relationship in embedded game environments. There was also another kind of project that's still based on puns on dishes, which was about dish constructing the dish brain. Basically, the idea is that we train a multi-layer predictive coding neural network to predict the up or down state of the panel based on the input spikes that we're recording by the people at Cortical Lab. And then these are self-invertible neural networks. So then once you add that, you can just say up or down to the network, and it's going to feed you back spikes. It's a very nice problem that you can, it converges very nicely, both for naive, like these unlearned dishes, and for smart dishes that have learned how to play Pong. And basically what you have at the end of that is that you just have like an up or down command, and then you can regenerate a bunch of spike trains that you can think of like re-injecting into the network to give it commands afterwards. That's a tall order, and I don't know if the people of Cortical Lab will ever answer my mails, so But basically, what's going on is that you regenerate patterns of spike at the end. This is the cosine similarity between the up and down paddle representation for naive dishes. And after the game has learned, it learns how to split its representation to be a bit more dissimilar. This also begs the question that Andreas and the people of the Cortical Lab have been working on, which was trying to understand what the dish actually learns. So they had like a quick presentation during the NIT demo session where you can see that the mean information entropy in gameplay on top. So it diminishes actually. Oh wait, that's the entropy, that's good. So the mean entropy decreases about at the 10-minute marks, and the firing sparsity during gameplay increases as the dish is learning. So we still don't really know after all these trials and error what the dish does, but we have a bunch of cool demos. Lame dish-related pun that was too shy today to tell them all in front of you, but hopefully you read them on top of the slide. And we also had like some useful scientific project, basically the idea that we have like some sort of dish simulator that we can either benchmark in terms of reinforcement learning agent versus the dish, or use to dish construct the dish and then try to understand what's going on. If you guys want to check out, we have a nice, very well-named GitHub repository. Everything's commented, and there's like a bunch of tutorial notebook that will walk you through everything.
Everyone.
Sorry? Okay, and I think I'm done, yeah? Woo! Yep. All right.
Okay, everyone. The idea of our project was to use joint encoding for continuous gesture learning, and using like this dataset, the HP19, for like decoding the joints of people performing various actions, and train a kind of general encoder that could be also put on spec, and then use the general encoder to train a latent replay model for continuous learning of new poses and new motions. So that was pretty much the idea. As you can see, like lovely sketch here. Yes, the problem was that we didn't get it to generalize well on the data set. So we don't understand whether it was a problem on the data set. This is data, this is the same model trained on getting the joint positions for like a person on the original data set. But sadly, this is what we got on the actual hardware or on the camera. So there are some joints, but there is also a lot of weird stuff happening, especially here in the corner, which we don't understand. There is a difference between the original dataset and this one. There was like more stuff happening in the background. And it's more noisy. Maybe the camera is different. So I guess we have a problem of actually the context and maybe some overfit. And also we tried to, okay. Okay.
Yeah, that was for the encoding part. And then the other aspect, we're trying to see what we can do with this continuous learning approach. This is something very typical in the field, to see if we can learn typically new classes on top of the pre-trained one with a few samples. And we're focusing on this recent paper and approach that is basically saying if you store some of your inputs from your pre-training from your original classes in the latent replay space, so in latent space, as a latent replay, you can reuse this information to keep training new classes, but you use little memory, you limit the memory usage that you have. So it's really a good match for like tiny ML, like neuromorphic hardware. And what we wanted to contribute to that is to say, okay, what happens now if we try to put that into even-based data? So what we took now as a concept was the DVS gesture data set. So just this end gestures to be recognized, to be classified. And we got a proof of concept already working using this approach on this data set with very limited pre-training. These are not the state-of-the-art accuracy at all in this data set. We're using only 5 classes, with few pre-training samples. We were starting at 90% accuracy, and then starting to add with few extra samples, only 200 per new class, trying to add class using this method. And we got some performance where, you got a decay, of course, in the full accuracy, but you're still maintaining some performance on the whole classes, although you have only a few samples, thanks to the latent replay and this regularization that is introduced here. So we're going down into 81% accuracy, adding 3 classes, and they only add 200 samples each. Just to have an order of idea, this is like 10 seconds of recording. And so this is not fully like complete. We are trying also with integration for the demo with spec. But the further step, things we want to explore is to say, okay, now we have even-based data. How can we optimize maybe this latent replay even more? How can we limit the data storage? Maybe using sparsity of events, things like that. Something we want to explore. And also having maybe, because this is all doing backpropagation. If you have events, you need to go through time. So we're also thinking maybe having simpler learning rules like the LGBT propagation could help simplify this for neuromorphic hardware. So yeah, that's a bit the further steps in addition to updating, improving the encoder that we want to keep on working after the workshop. Yeah, that's it.
Hey guys, I'll just fly through this slide and we have more fun stuff later on. So what happens here is, imagine you have a gesture-based model similar to ChatGPT. I mean, it's not that good, but it's deployed at your backyard. And it's able to detect all kinds of gestures in general, but it's not customized for yourself. So a lot of times you want to fine tune the model for yourself so that later on it's better for detecting your own motions and your own gestures. And the other problem comes as a lot of times we don't know how to label the data. So the process we have here is we record the data, we record voice from Xylo to label the data for us. And then we actually record the motions, the DBS motions using spec. And we train like a feed-forward multi-layer perception network to classify the voice. And we have another feed-forward spiking convolutional network to do the gesture detection for the motions. And yeah, I'll just go to the fun stuff. And so what happens here is I'll show the video of Jason going through the whole process.
I did not consent.
Sorry. So the first step is, it's lagging a bit. The first step is you go to the model, you create a label using your voice. So I think Jason saved up here. And then this is the pattern of his song. And the label here is not seeable, but it's actually up. And now Jason is doing jumping jacks. He's warming up, sorry. He's warming up with this. He's warming up with this. He's really fit. Yeah. So Jason's too good for our model. Our model is really, really lame. We're not fit at all. So after that, we recorded his data in real time. We feed it into the model. Yeah, now it's training. So there's a progress bar for training. And so I think I'm trying to print the accuracy, the testing accuracy on a pre-trained data. On a pre-recorded data set. Wait, so we missed the best part. So basically, let me explain it. So after we trained, the accuracy dropped down a lot just because of Jason's recordings. So, anyways, we're still trying to fine tune the model as if you do more burpees, the accuracy goes up more. So Jason, next time burpees. But anyways, the idea here is the model is fine-tuned using every new sample, and the learning result is kept from all the samples while we don't really keep the data. So it's like meeting people's privacy requirements, and you can do really easy labeling just using your voice inputs. And yeah, wait, let's see, go on. Oops, wait. I started playing again. Okay. Oh, cool. Yeah. So this is the idea when we actually try to use our pre-recorded data to do more training. So this is accuracy. The accuracy goes up when we do more recording. We include more data sets, and then the loss goes down. And so it's practically possible. And we also have more outlooking. So we want to do real-time sensing instead of record the data and feed it in. But right now, the pipeline is not built yet for us. So we will try to work on it later on. And also, we would like to do something similar to Maxime and Marco. We want to do incremental learning for more gestures in addition to jumping jacks and burpees. And ideally, the third point is kind of similar to the first point. We want to map the whole process to the hardware. So right now, we still have to extract the data from the hardware, process them a bit, feed them back to do the calculation. Hopefully, the whole process could be done on the chip. And we want to also explore more online learning algorithms. And we can also include more sensory data and just to do more fitness monitoring or something like that. Yeah, awesome.
Hello, everyone. Okay, our project is very ambitious. We believe that every team, every researcher, every user deserves its own custom hardware for its spiking the neural network. Why? Because every user has different constraints in terms of area, processing, time, and power consumption. So we want to provide a configuration panel when the user can put the network topology, such as the number of layers, the type of neuron, etc., and other specifications such as the number of hardware synapses and neuron. This will output an RTR description, an hardware description that can be implemented on FPGA or an ASIC. Okay, so first of all, we have implemented a parameterized design, a parameterized RTR description where we can put the number of neurons for a fully connected spiking neural network. When we can put the number of neurons, of layers, the decay threshold, and so on. And for the tiny tape out, we implemented one neuron with 32 tiles synapses in Skywater technology. And we compared our custom design with non-optimized design. And we found that our design is better in terms of total cells and power compared to the standard design. And then we tried to implement the spiking neural network with the 3 layers on FPGA. These are the results. And we want to continue to add other option and configuration option to.
So we're here to talk about a pain that most of us are probably having. And the pain obviously is that we are faced with like 1 million. Let me go one back, going on. You're ruining my pun here. So the pain obviously is that we have so many simulators and we have so many different ways of. The pain basically is that there are so many different simulators, as you all know, and many of them are, doing a really, really good job. But of course, we want to have a single simulator to do one good job, and so we can convert between the simulator and the hardware. So of course, our solution is to create another simulator, so we now have even more simulators. Of course, that's the joke. Exactly, that's the joke. I have a problem saving my slides here. I mean, Zoom is crashing for some reason. So if you can move forward to the side. Yeah. Of course, we're gonna bandwagon with all the defunct standards and ways of unifying this field, just like Planet ONX. This is, of course, a joke. And here's the solution that I think is slightly more serious. If you can step ahead. We had some wonderful talks in the past weeks about how we can simplify the integration between all these simulators and neuromorphic platforms. And I think there's a silver lining here I'd love to communicate with you. And so a lot of smart people have been discussing how to work on this. And it turns out we all have a common language. We have a common mathematical understanding we can revert to. And that understanding is ODEs. So what we've done, what we've done here, if it was slowly going, is that we've tried to define some common primitives, some common operators that works in simulation as well as in hardware. And this is different from previous efforts because we have a mathematical foundation. It's also different from what the machine learning community is doing because they don't care about ODEs and time. They care about computing primitives they can put on TPUs or DPUs, IPUs, whatever. Yeah, maybe, I don't know if you want to.
So yeah, our approach kind of balances both, the kind of technical feasibility of implementing all of this stuff. By going into ODEs, we're abstracting away a lot of issues regarding discretization and things like that. And we're also moving a lot closer to physics, so that will allow us in the long term to also move into analog, mixed signal neuromorphic, and also other platforms like photonic or other kinds of systems. So that's kind of the long-term vision. And the current state is that we're already supported by 7 platforms, mostly supported, let's say. So you can see on top, there's the simulators that you can put into NIR and also get out of NIR. And then on the bottom, we have the hardware backends that will also demo, right?
Yes. Yeah. So now I'll try to share my screen again.
Keeping the mouse in the way. Here we are, the gate. What do we got? Over here, we have this from the neural modeling approach that I tend to use, which is Nango. We have a description of a neural network that is a recurrent neural network that approximates the Lorenz attractor, just as an arbitrary task. And we can take, this is just like the exact code from just like one Nango tutorial. And then if we, somewhere up here, there is all this code to go and convert it into the NIR format, and then code to convert it from the NIR format back into Nango so that we can actually run it again just inside the system, just to show that we can do the full conversion in and out. And if I press play, just to show that the whole system works. So can I, there we are. Nice. Over on time. So, going through the whole conversion process, we still have a bunch of spiking neurons, and this is the subspace that those neurons are representing, and it worked. So we were able to convert in and out, and everything worked fine. Is there anything else I wanted to show? Okay.
So tell how to use NIR now to improve Nango or to make it faster?
To me, it's more about interoperability. If people have design models in one format or another format, and I want to build things to stable it all together, I see.
Yeah. So this is basically just to give a brief example of like how you could use the NR representation to convert in between frameworks. So let's say you're committed to one framework, such as one of the many that are supported, SNN Torch, Nose, and Nango, and so you want to train your model in there. So what we have here, okay, we start off here with the Nose model. This is, how it's defined. We have like some connectivity and integrated fine neurons. You might want to train this, however what you're familiar with, and then by simply calling Nose.torch.toNear, you will convert this model into our near representation which is defined by graphs and by nodes and edges. And then we can go to any of these other support frameworks, such as Synapse, and we can call from near. And because now this near graph is like standardized and supported by all these frameworks, we can basically translate from one framework to another. And once we have our model then imported in Synapse, we can convert it to make it compatible with spec, and then run this thing and deploy this thing on spec, even though we're trained in Nose. So whatever framework you're familiar with, that means then that you will be able to kind of like convert between frameworks that support the hardware that you are interested in. That's all I wanted to show. Thank you.
Yes.
I think.
Like ONX.
Yep.
But in continuous time.
And better.
So I think I want to attach one more point to this. First of all, credit to the amazing effort done across the board at this work. I'm absolutely baffled by the convergence on this tool here. It's been amazing from all these people here. Stephen, Terry, Peng, Gregor, Felix, Sadiq, Jason, Matthias. So thank you so much for all the effort. I think what's exciting here is, first of all, this is a declaration, right? I mean, we're literally just working with physical primitives. And so for domains such as Kubo optimization or even icing model, something else, this can be really, really fun to play with. And we want to really push this further down to physics because, physics are just differential equations. So that will be fun to continue in the future.
I just want to say that Jens actually really pushed this one. I learned that he didn't go on a single hack and in order to late nights to push this thing forward. So I think give it up for Jens. Which screen is not shared?
Maybe just use
So I'm not quite done because
you need to hurry through this one.
I want to hurry up through this one. So I can do it very, very brief. Like another infrastructure problem is to stream events through infrastructure, right? So in Stockholm, we've been doing a lot because we work with event-based camera, and Sadiq from Synthesis and Felix and Gregor have this wonderful platform that we want to use. So we just want to plug this into this infrastructure. And the reason why this is really cool is because we can directly work with this in our favorite tool chain, namely Python. And I know that Maxim and Marco, sorry, I was blanking there. work with this to stream events into PyTorch. And that means you can run your PyTorch model directly, which is kind of cool. And so what I want to show you very quickly, because it flunked the other day, is that I can actually stream this now. So here we have a spec chip running, okay? I'm gonna switch to my terminal. And this is a live spec event stream from Python. Thanks, you made it well. Yeah, so what's only left to say, and then I'm done, is basically that I think this is a wonderful community effort again, and I can't wait to adopt this. I'm visiting European Space Agency in a minute, and they're going to use this. And I hope like we can come together, the community, also to make this easy, because then the next generation of PhDs does not have to suffer the same pain, and we can really like prove that neuromorphic technology actually can be adopted and work, not just a pipe dream. So thank you.
Another project we worked on was playing with generative models. You might be familiar with these image generators like Midjourney, where you put in some text and you generate like high quality images. Maybe you want to do a style transfer of your image if you input another kind of image, or you can even generate, from audio, go to text, or, all these combinations possible. So these state-of-the-art models are called diffusion models, because what they do is they first destroy an image by adding noise over multiple time steps, and then you use a kind of like autoencoder network to learn to reconstruct the noise, so that it learns in this case, the image embedding. And then during the prediction time, during the sampling time, you can then you reverse the process, start from noise, and you can kind of like step by step subtract the noise to generate these high quality images. So I just want to clear things up. These are the original images, and these are our high resolution crisp generated images. The idea was to play with different event representation, because if you just have events, then sometimes it's helpful to generate, like images for if you do calibration, or if you just want to get some new colors that were not in your original data set, also very good. We're gonna have to develop this network a bit further, maybe like increase the complexity a bit to get the quality a bit further up. But that's what we did.
Guido played a little bit with the fireworks data that we gathered at the fireworks, and what we're seeing there on the right is just the time of these, one of these fireworks explosions you can see on the left, and the time is on the vertical axis here. It was just fascinating to go play with the data, just because you get this incredible burst of events right at the moment that the firework goes off. And then whether that's reflection off the cloud or possibly weird artifacts in the camera, who knows? But then Guido was getting, do you want to say anything about?
Yeah, sure.
So I think a lot of you have seen this figure already, this cartoon on the left. Actually made the rounds at the workshop here in a talk yesterday, and kind of in popular media sometime this year. Basically, it's a cartoon from 1923 of newspaper cartoonists, and it's kind of making fun of how electricity is going to solve all of his problems, and basically come up with the ideas and make the cartoon for him. So kind of circulated recently, since now we have ChatGPT, stable diffusion, and whatnot. And so we're kind of at this reality 100 years later, where we can have these tools generate kind of cartoons and graphics for us. So kind of a natural question for us at the workshop: how well can these tools generate neuromorphic hardware? So basically this started with asking ChatGPT to write a Verilog model of a leaky integrate and fire neuron. And it was actually pretty decent. The code is able, or the kind of model is able to generate correct, so that's functional and synthesizable, like hierarchical Verilog. So I'll wait for the next slide to transition. Basically, I'm able to ask the model to both generate a module and then instantiate that module within other modules. So kind of this hierarchical Verilog, as in like a typical design flow. So we have this single neuron model, which is then instantiated in kind of a fully connected network with 6 neurons. You can both kind of modify the design through prompting, like, hey, can you quantize the weights a bit more? Or can you set the weights to be 4-bit values instead of 16 bits? You can also extend this by asking it to make the weights programmable and things like that. One of the kind of interesting conclusions here is kind of as the scale gets larger, so kind of more complicated modules, multiple modules, deeper levels of hierarchy, the model kind of starts to make mistakes and kind of loses kind of that broader sense of context and doesn't really understand how to connect things anymore. But kind of at the end, we're able to produce kind of a full layout. Wait for you guys to see the screen with no human code changes. So basically directly copy and pasting the code from ChatGPT into these open source tools. The final model was 2 layers of 3 neurons, which were fully connected. So there was 9 programmable weights. Nothing. Basically, there's a simple interface with like a weight select. You give the weight and like a load enable type signal. The backend flow is completed using the Google Colab notebook with the open lane flow developed by Jason. The final design was 225 micron, about 225 micron for 6 neurons and 9 synapses, which isn't too impressive, but kind of the standard tricks that we all are familiar with could be used to improve this, probably through prompting ChatGPT, asking it to quantize the weights more, replacing multipliers with shifts, and things like that. But kind of the real punchline here is we're able to go kind of through a whole design flow and get something that will work, basically using ChatGPT to generate the design kind of from scratch, which is kind of incredible. Asynchronous design using ACT. Again, there's a bit of a lag between the slides, but I think a number of us were at the talk from Rajat Manohar on his asynchronous design toolkit. And so basically I kind of took that through this workshop and just kind of experimented with it a little bit. So there's kind of a number of different input modalities, be it CHP, which stands for communicating hardware processes, or production rule sets. And there's also a number of different circuit families. So I kind of just got myself familiar with his tool flow.
Just explain.
All right, yeah, so I mean, just a picture of some code and simulation in Rajat's ACT flow framework, which is all well and good. This gives you a simple design for an accumulator, and you can take this design, go all the way through the place and route flow. And now, in theory, there's a picture of some nice layout that's all nice and routed and kind of shows completing the design flow. All right, and basically I showed a couple other pictures of a couple of different designs that I went through this flow with. There you go. I'll probably progress to the other slides shortly. But basically, I just wanted to look at kind of for these different circuit families, so that's bundled data versus quasi-delay insensitive, like what are the different area trade-offs that you can make? And is there an area of benefit to kind of writing the PRS or the lower level description from scratch? And yeah, so I made a bunch of different designs, laid them out, and kind of getting myself familiar with the framework.
So as you can see in our first slide, we have a group picture, and we have the names of our participants. And the order of the names is the order of the people shown up in the photo from left to right. And also put the names who weren't shown up in the photo. So I apologize if I missed your name. Okay, let's start. Okay, so first of all, I want to revisit our focus and goals. So we want to bring together neuromorphic and conventional sensors, including the DVS, dynamic vision sensor, a traditional RGB camera, together with embedded platforms, including FPGAs and also Spinnaker 2, to run neural networks for nonlinear neuromorphic control of robotic platforms. And we have 3 main project themes this year, including neuromorphic eye control. We collect some data set from participants of our workshop. And we also have projects of car racing using the Invincible. I think that it's a platform developed by a big team led by Toby and Marcin for 2 years. Yep. Okay, let's skip this part. We also have a carpal platform, which is nice to test different control algorithms. It's a nice platform because it seems simple, but not too simple. So when the pole angle is approximately vertical, the small change of the angle and the position of the car is easy to predict. So the system kind of linear. But once the pole falls farther away from the vertical position, things get more complex. So let's start with our first demo from Kinyu about neuromorphic eye control.
Yeah, so this project is about neuromorphic eye tracking game, Feed the Hungry Mouse. I believe a lot of you guys just played the game yesterday. Just raise your hand. Yeah, I believe a lot of them are not here, right? Okay, so here we use a DVS camera to capture your eye movement and try to transform your eye movement into somehow a gaming control mechanism by predicting the the pupil center of your eyes. And here we use a CNN model with 5 convolutional layers and 2 fully connected layers. So here you see here's the input. The input of this network is the event stream from those previous camera, and output is XY coordinates of your pupil center. And in this game, your job is to help this hungry mouse eat as much falling fruit as possible. Just simply move your eyes and change your eye gaze. So here is the result, the prediction result when someone's playing this game. We can see that there are about 3 levels of the X position because we only set 3 lengths for those falling fruit. That's why we have 3 levels of this X prediction result. Yeah. And then in addition to this, we also collect some eye movement data from our lovely volunteers. We asked them to do 5 kinds of eye movement. The first is just the feel free to move your eyeballs. And the y-axis is the precision and the x-axis is the time. And the second is the second between 2 points. And the third is we ask them to read some text and we record their eye movement data. And the first is smooth pursuit. The final one is just feel free to blink your eyes. So you see this blue dot, the dark blue dots, this blue dot means someone is blinking and otherwise it's not. So I'm trying to make this data set clean and precise and hope it can contribute a little bit to the even best eye tracking field. Yeah.
Okay, good morning, everyone. So I decided to present, even if we don't have many quantitative results in the philosophy of our topic area. So I would like to start from like a survey. So how many of you tried yesterday demo? Raise the hand, okay. How many of you won against the Invincible? Okay, so that meant that it was not so easy to drive the car, even for a human. And what we are trying to do for our project is to, because at the moment, the car is driven by using LiDAR readings for that estimation. We are aiming to implement an algorithm to do DVS, so base control using event cameras. So that's why we started to integrate in the platform, as you can see from this video. An event camera actually was a stereo camera, so thanks Terry for lending us the infrastructure. And we managed to collect some data from event cameras in a stereo mono camera setup. As you can see from this video, you have the left and right output of the camera. So we have a data set along with also other data using ROS to subscribe to different topics like ground truth from different sensors, or also the throttle and the string angle. In the future, we're looking forward to implement different ideas. For example, trying to estimate the optical flow using maybe neuromorphic platforms to give maybe contribution to the novelty in the scientific community. Or we have another idea to learn the direct mapping between the events and the sparking and the steering angle and throttle. And so I would like to thank Toby for giving us the opportunity to use this expensive hardware, and also to Marcin that developed all in the infrastructure. Thanks for the attention.
Now we move on to a series of carpal projects. We have a lot of carpal projects. So the first series is called Learned Control. So first I want to ask a question. So yesterday, how many people have tried the toy made by Toby to balance the carpal? Okay. And I would say that I didn't see anyone could balance it make it steady for more than 3 seconds. So I would say it's not an easy task. So in this project, what we're trying to do is to basically train the neural network to learn how to control. And the first thing we tried is to imitate a nonlinear model predicted control. Basically try to train neural network to play copycat. And in this project, we use 2 different networks, spiking delta RN, imitating the classical controller, and also a tiny feed-forward network to do the same thing. And we also tried reinforcement learning by the Spinnaker 2 team. So they use their Spinnaker 2 brain-like chip to run a network to be trained with trial and error. So the system looks like this. We collect the carpal state including the position from the encoder of the motor, and also the angle from the potentiometer on the card. And these carpal state will be sent to the hardware. And hardware will run the neural network to generate the control signal, which is the force and also direction applied onto the card. And now let's start with our first carpal project. Yep. Let's welcome Antonio.
So our question here is, can we design a neural network controller to be deployed on neuromorphic hardware of FPGA to control the physical carpal? So the system that we have this year is a system chip FPGA, where in the processing system we have a microcontroller and the memory, and through the axis bus is connected to the FPGA. So here we deployed the network that Charlie mentioned before. So the temporally sparsed data GRU network is has 7 inputs, 2 heavy layers with 128 units and 1 output. This is deployed in the Delta RNA accelerator, and the multi-layer perceptor network is 7 input because it's the physical carpal current state with 2 heavy layers with 16 each and 1 output. So our result is in the smaller system of FPGA that you can find that is around 80 watts with USB 2 volt. We have some result for each controller. For the MMP, that we have 416 parameters. We get almost the half of the FPGA. This is because the MMP is almost fully enrolled. And the computation latency is around 1.5 microseconds. You see only 35 milliwatt. And on the other hand, we have the accelerator, the HDRNA, that it's using 15K parameters. It takes only the 20% of the FPGA. The latency is 8 microseconds, and well, we have almost the double of the power consumption. So the main difference between the MMP and the HDRNA, that's all of these parameters in that version are hard-coded during the synthesis. So you cannot change the parameter of the network. But here in the accelerator, we can change from the PS all the parameters of our network. And yeah, and that's it. So in the behavior in the robot from both controllers are almost the same.
Thank you, Antonio. And here's our second carpal project, which is called latency robust control through data augmentation. So, in a carpal system, if you want to achieve good control, you have to make sure that system has quick responses. So basically, you need a low latency between the sensory data to the control signal applied to the card. But sometimes it's not feasible to achieve low latency. For example, if you want to do a remote control, or the controller is simply too complex to be computed within a short time window. So we found a way that we can make the controller more robust against long latency, even with imitation learning. So the way we train our network is sequence-to-sequence learning. So basically, we feed the network with the sequence of the states, and we want the network to generate the sequence of the force applied to the part. So a small trick we use is called time shift augmentation. So basically, we made multiple copies of the same dataset, and we merge them into a bigger dataset. But simultaneously, we deliberately introduced a 20 millisecond latency between each one of the subset. And by doing this, we train the same network to generate the same output sequence, and we can make the network more robust against long latency. And here is our demo video. So here are 2 videos showing the MPC and also the GRU imitator with a 60 millisecond latency between the sensor and the control signal. So as you can see, the GRU imitator can quickly make the carpal steady, but the MPC couldn't make the carpal steady in a short time period. So actually, I Googled the latency between different continents, and I found out that the latency between Argentina and US is around 100 milliseconds. So actually, the best we could do is to achieve a 100 millisecond latency control of the GRU imitator.
Yeah, so in this project, we were trying to, the question was, can we get Spinnaker to control a real physical system, in this case, the physical card pull, and can we do this in real time? So this has been challenging because it has never been done before on Spinnaker. So Spinnaker has mainly used to do like batch simulations. You give an entire data set and then you get your results. So this was like a new application on how to use Spinnaker.
Spinnaker 2.
Yeah. So we took a different approach. Instead of training an imitating network, we trained a reinforcement learning agent from scratch using TP3. And here you see the training curve. So these are the number of episodes and the rewards you get. After about 1,000 episodes, we get stable rewards. And then we took this network, and then Matthias, you can say more about how you put it up to Spinnaker.
Yeah, so basically, at first we wanted to implement a spiking neural network, but because there we have quite a nice framework, so we can just load the network in a Python framework and just say, okay, deploy on Spinnaker, and it will do that automatically. However, that framework, as Mahmoud said, this framework is primarily made for batch simulation. And yeah, so getting this to work in real time is still quite a bit more software development effort. So instead, in the middle of the workshop, we decided to go another route to implement an MLP basically in low-level software, just write the Python code, the C code, sorry. And so we basically implemented this model in software on one of the cores. So maybe you can go to the next slide. Yeah. So yeah, the neural network that we have has 2 hidden layers with 64 neurons each, so about 4,500 parameters. This is running in really just in software in one of the 152 processors on chip. The computation latency, meaning we send the state from the laptop to Spinnaker and receive the final result. So that's in the amount of force that the motor should be doing. We get this in about 0.8 milliseconds. However, the total control loop takes 8 milliseconds. So we set it to 8 milliseconds because the control framework for this card pull is running in Python, and there's quite a bit more going on there. So basically just the Python code running on the laptop, forwarding the data to the actual physical card pull takes about 6 milliseconds. So yeah, we're by far not limited by the Spinnaker here. And yeah.
But this was fine to control the physical card pull. Exactly. Because you need like 20 milliseconds is enough to control it. Really fun.
So in the beginning, we actually tried 20 milliseconds. And we found, yeah, we can reduce it to 8 milliseconds, and it got even more stable. For the future, so what do we learn from that? We only need 1 PE to do this control now. So you have 151 PEs available to do other tasks. So you could think of using this for controlling really some robots.
Or you can control how they handle two catapults.
Or that, yes. However, we didn't even use a lot of the Spinnaker features. So we did not use any of the accelerators for that. No.
This was C code. This got C code running around.
Yes. Yes. So if you use like the matrix multiplication accelerator, you could reduce the computation latency again by a factor of 5 to 10 at least. Or you could run much bigger networks in the same time.
Okay, here comes our second set of carpool projects, learning to adapt to unseen scenarios. So the question here is, what if you have changing pole lengths, and can we adapt the controller to unseen scenarios? So we have projects to predict changing pole lengths, and also projects to adapt neural controllers for unseen pole lengths by happy learning. So let's move on to the first project by Jinming.
So this project is about adaptation for carpool to constantly changing pole length. And for this project, I mainly want to answer 2 questions. So first, can we actually train a network that helps adaptation to changing pole length? And secondly, if that works, what is the actual limit? So the method is to train a simple multi-layer perceptron that takes the past state, the past control, and the current state, And from that, it can build the relationship through the card pole model to find to figure out the pole length. And with that pole length, we then feed that. Quite a lot of latency. We then feed that onto the MPC to generate the control output and put that onto the card pole system. And finally, we took the control output and the state from the card pole system to feed back onto the input of the network. And to inject noises into the system, we took a random walk approach on the card pole length, where the pole length is able to change plus and minus 10% for every time step. And this is our results, where the dashed line are the ground truth of the card pole length showing on the y-axis, and the x-axis would be the change of time. And the dots are the prediction outcome from the network, and it's kind of fits to this to the ground truth. And it needs to be mentioned that in this setup, the random walk time step is 0.01 seconds, which is half of the MPC updates interval. But the network is still able to predict, because the 2 time steps later, because of the random walk process, the card pole is still kind of related to the original pole length. And this is the card pole with this setup on the fly. You can see that the pole length is jittering quite a lot. It's quite funny to watch. Because of this crazy noise, it kind of takes a solid minute to swing up and converge and stabilize at the target position. I know a lot of you would start to wonder, what can this be useful? There is no shifting pole that's in the physical world. So the actual inspiration would actually come from the memory search, where we have a crazy noisy filaments in that it constantly changes shapes upon external voltage apply and also physical diffusion. And with this setup, we might be able to predict the hidden noisy variables, for example, the geometry of the filaments, that can actually affect the memory dynamics. And maybe we could build some algorithm that is more efficient than the nested loops that is commonly used in memory write and verify algorithms.
Hi, everyone. In our project, we are using a virtual simulation of the card pole by OpenAI IGN. So the task is to keep the pole upwards, actually, not to swing up, but simply keep it upwards. And the question that we asked is, can we augment traditional NLP with a Hebbian component to the connections such that it generalizes better to changing pole lengths after training to keep on still balancing the couple? So to do that, we simply wrote a simple PD controller, proportional derivative controller, to balance the carpool with a fixed length size. From that, to generate many simulation data to train 2 networks. So both, as I said, a regular multi-layer perceptron and a multi-layer perceptron that for each connection in the network, you have this thing here, which is simply a function of the activations of the pre and the postsynaptic units. It's a product of these 2 activations. And during training, both the weights of the connections and this alpha term that is basically scaling up and down the Hebbian connections are being trained by backpropagation. So we want to see if after training on this fixed pole length from a PID controller, so after you learn to imitate the PID controller for a fixed pole length, can you change the pole length of the card and still have the networks that learn to imitate the PD controllers working better? Yeah, so these are results. So basically, I think it's what. In blue, you see the PD controller. So this is performance on the task as a function of pole length. So the network was trained on data generated on pole length is 0.5. And so the PD controller only works for this particular pole length. Then a normal A&M, which is in orange, works generalizing into the pole length of 1.5, while our Hebbian, which is in green, generalizes until 2.25. So in keep going. Yeah. So final results we saw was the Hebbian component
gives us around a 2.5 times X performance gain versus the ANN, and a 4.5 performance gain versus just the PD controller.
So to summarize
you were running the whole time?
Yeah, so the head component is not a weight that is being learned, it's simply a dynamic adaptation. Yeah, so it's a term in the connection that is constantly changing with as a function of the activations of the units it connects to.
So I think it would be interesting to compare the PID parameters being controlled by a neural network that learns the dynamics. So the PID controlled parameters learn online by your changing.
Yeah, that would be interesting.
I mean, we're still actually understanding why it works better. We hope it wouldn't. And we want to do further analysis. For instance, how much do we have to increase the ANN in parameters to match the Hebbian one?
And the ANN, just to, the topology and the number of neurons are identical between the Hebbian and the ANN.
Okay, our next project is online RL for particle balancing.
Don't look at the slide. This is something we discussed a lot with Mahmoud. So it's two people project. But the point there was to try to have a pure RL approach. So go the hard way on this, and we're going to see that this led to limited results. But the point was to see can we try to use to learn as the Hebbian case online. So dynamically, the weight of the network of the ANN to be able to control the carpool with this actor-critic representation, which is the fact that our network is associating value to the current state of the carpool, and with that is able to determine a kind of dopamine signal that will allow to define the update of the weights for the action, for the actions that will be defined for balancing the carpool, and then And the idea was then to use that in an online case with a very simple learning rule, which is the Delta learning rule, something that Terry has been implementing in one of his papers, just using basically the weight update is just based on this dopamine signal that you get online and based on the trace of your representation layer, hidden layer, and your action layer. So very simple rule, simple reinforcement learning scheme. The point was to balance the carpool. And the protocol was the following. So here the training is with reinforcement learning from the start. Probably makes it harder, but using also the actor-critic system, but with backpropagation, we pre-train this actor and this value network. And then we just multiply the carpool length by 3 and see how we can adapt. So these are the original performance of the pre-trained network with adaptation. So in a number of episodes, so our repetitions, you can see that the average number of balance steps only reaches up to 20 steps. So it's catastrophically failing. But having this online adaptation with this actor-critic online rule, we get other episodes. So that's a big limit with respect to the project to William, with respect to the project of William and Thomas. The fact that we need here, you can see at least 3 episodes to be able to balance. So if you just run it once, it's going to fail first, a second time, and then the third time, it can reach the maximum number of steps, 500 steps, and then it fails again. But so it's kind of mitigated results. So it kind of works, but not fully. There's still problems of stability. Also, when we want to stop the learning, so we see it works, but then it crashes again because it keeps learning. So probably there should be added some covenants to stop the learning when it converges. And yeah, just to conclude, kind of a take on massive is online reinforcement learning is hard. It works better also to pre-train maybe with some normal controller things, go towards hierarchical approaches, and maybe with more pre-training could do something better. And that's I just wanted to show at the end I tried to do some meta training on top of it, so pre-train considering that we would have this online adaptation, and it's not fully conclusive yet. Something I want to keep exploring.
Next, we have our last project.
So this is a perfect thing to pick up, because even though we are beating the dead horse that is known as carpool balancing, we believe there's some interesting work in the meta-learning domain and in the continuous domain. So let me briefly explain that, as Maxime says, like RL is quite hard.
And it's difficult because you want to learn a good policy to maximize reward, but if you want to operate with real robots, you have to do that in time, right? And time and recurrence is just notoriously difficult. So we've taken inspiration from the wonderful work of people here at the workshop on temporal memory units, so specifically Legendre memory units. It's a way to weigh the significance of past events for your present decision making, basically. So if you imagine this card pull here, and you can click forward, you're gonna get some, one step back, please. You're gonna get some input, some position, and one step back, please. Anyway, you're gonna get some positions and angles, and our idea basically is to try to learn a proper representation of that state in time. And basically what we're trying to do here is more or less an autoencoder setup, where we're using the temporal memory unit here to create a proper hidden representation to correctly predict the future state. And the idea then is, if you can go forward. The idea then is, one more please, to actually use that in a policy learning like Maxime suggested, because then we can use that correct representation to simplify the actually policy learning in an online real reinforcement learning setting. And so the preliminary results is that we are actually quite on par when we learn to predict the full state in blue versus the partial state in orange, where we remove all the derivatives, because the derivatives are not physical. You don't really measure that in actual robots, but that's exactly what we get when we use the kind of temporal memory recurrence. So that's pretty much what we have now. We have preliminary results on the reinforcement learning setup, but that's what we're going to work on towards the next couple of months. Stephen Abreu did a lot of the coding work here. Unfortunately, he's only with us in spirit and Zoom right now because he has to leave, but he should really be credited for a lot of the work here.
So let's wrap up. So this year, we have made some very nice step forward. For example, we have introduced the Carpo platform to a large group of people. So the Carpo platform was first brought to Telluride back in 2019. And this year, we're having many more people and projects using this platform to evaluate their control algorithms using imitation learning, reinforcement learning, habit learning. And I think one of the biggest step forward this year is that we moved from playing a simple computer game to use hardware to control real physical stuff. So we have made use of FPGA and Spinnaker 2 to use hardware accelerated neural networks to control a physical carpal. And I think a good future direction could be that we build hardware to do online learning to make the controller perform better on fly. And finally, I want to thank all the members of our NC23 topic area, and also thank you all the participants of the Telluride Neuromorphic workshop.
The case of speech and music. So I don't know if you remember, we set a couple of goals in the beginning of the workshop. Mainly it was to establish the methodological and the conceptual tools to investigate speech and music production, and also multimodal perception. So what we focused, I feel like there is an echo. Doesn't matter. What we focused on was to establish some robust EEG measures for real-time analysis, also some robust denoising technique using different strategy, explore new methods to characterize precise speech music production activities, implement a working real-time closed loop using EEG data to drive only with your brain. And also we looked into establishing models for tracking or tackling multimodal processing in complex naturalistic scenes.
Thanks, Claire. So some big picture questions to keep in mind. Overall, we're interested in understanding this bit of matter between our ears. High-level questions: what are the cognitive processes that are involved in planning, in attending, in these activities? What are the limitations to our ability to learn how to control our motor actions, to create speech and music, as well as other engagements with the world? How does expertise shape these abilities? Some of the work that you're going to see will look into this question. And then we're measuring EEG, as well as there's some additional data sets that folks have worked on during the workshop, so that we could try to identify the neural correlates that underlie these processes that we're asking questions about. And importantly, we're building systems and paradigms that are going to allow us to interact with these underlying cognitive processes, new experimental paradigms and measurement techniques that we want to take forward beyond the workshop. So high level, think about this bit of matter as your controller. You have a set of plants that you control with that controller. Those plants obviously affect the state of the world. You take that state back in through the sensory system. And this is the big picture of what we're studying. And we're doing that through developing paradigms that involve music and speech, where we can manipulate the relationship between the action of the plant, the state of the world, and what is observed by the controller. We're also leveraging video games to do that as well. And in developing these tasks, we can disrupt these links. We can change how the plant affects the state of the world. We can perturb how the controller perceives the state of the world as well. And then finally, as Claire mentioned, we're also interested in building new plants that directly read from the brain to alter the state of the world, both because it's super fun to do, but also if you develop those new plants, you can start to ask these questions in really interesting ways. Turn it back over to Claire.
So we organized all the efforts of the workshop in those three main threads. So one was concerned with perception production, and we looked at the link between auditory reception and multiplying, and how this interacts with some prior knowledge that people may have, such as musical expertise or the familiarity with the language. And we were also, a big part of that was to tackle motor artifacts, such as the one that are captured in the EEG when people move, to enable robust decoding of the neural activity itself in the context of non-invasive PCIs, for instance. We also implemented different efforts to have EEG in closed and open loops. So we wonder what EEG cues can be used in real time. That's sort of like there is a fast buildup of the effect and robust enough so that we can actually track it using EEG-based PCIs. And we use that to track error during driving and decode real-time in auditory attention. And also actually in the context of driving, there's a lot of driving interest here. And finally, there was a thread that was interested in more analysis of complex auditory visual stimuli, such as films and video games. And here we were looking into how we can tackle multimodal integration in complex naturalistic scenes using different types of models to characterize auditory visual silency and things like that. So now I'm gonna turn to Tim, who's the one who starts explaining what we did with the piano.
Right. So they gave a great sciencey explanation of why we did all these things, but I like to call some of the thrusts we did were what happens when you mess with people when they're having fun. And so in that vein, we created the piano or the pay nano. And the basic idea is you have a keyboard, you're playing it, and I'm going to perturb the input or the output from the piano and then play back to you either the right key or the wrong key, either delayed, attenuated, or all three. One of the interesting things I think that we learned through this process was that even if you switch the keyboard, we sort of looked into, you move by 3 semitones, it makes the song sound really bad, but the timing's fine, and so a person can adapt to it and sort of stop listening to the keyboard. However, if you have an attenuation and a delay and changing of the keys, it becomes nearly impossible for an expert to keep time with themselves, which is a cool result. So this supported a lot of the experiments we did, and you'll see examples of this later. And then we also link this up to go to LSL, so all our 12 different data streams are all nice and lined up. And if you want to take this home and use it, it's on GitHub. So plug in a keyboard you want.
Okay. So I hope you heard a couple of raw notes, and what we did was we compared the reactions of the raw notes between novices, experts, and players. And every time you have this little flash bar running in the middle, that's the event, which is the exact moment when the wrong note occurs. And we wanted to compare the reactions of people who don't play piano, who do play piano but aren't playing, and then the player who has probably a really exact matching in their head and of what they expect. And then when that expectation is not met, there are going to be a lot of surprising responses.
Can you speak a little bit about it?
Yeah. So these are just kind of the average ERPs of all of the events where you have wrong notes. At the oranges are when you have an error, and the blues are just when you strike a note and the right note comes out. So for novices and experts, this is also noisy data that we have denoised. Some other people are going to talk from our group about the various denoising methods. And basically what we expected to see was no big difference between the ERPs of the novices, between the people with, between the reactions to normal notes and bad note backings. And with experts and players, you want to see a big difference between the ERPs of people with the error and not error. So we'll talk more about the denoising music. Well,
I don't need audio.
Sing along.
So the video that you were seeing with Wendy playing a very nice tone, that's not how usually pianists play. They go a little more dailies. And this is Matthias's hand being tracked by David Sandra from the control group. And as he's hitting these notes, these are the events that I'm showing with EEG data. And there's also a glove with an IMU on it that we're tracking out. The goal is every time any of these events happen, you see some of this like bad stuff comes along. That's because of the motion that's coming along when you're moving. You're trying to play these different keys. And our goal is, if we take this data, so usually we take like all these key presses, we try to align them up as, think of this like an oscilloscope that is averaging your data, and these are the events. And we want to look for something like motor planning just before you hit a key, and an auditory response just after. Instead, what we get is garbage, because all of this other stuff creeps in, and if you're just averaging and you have these big deviations, things are just going to go to hell. And now our goal was, how do we use this like sensory stream or some other heuristical method to denoise the EEG to be able to recover something that looks like real brain data? So going on, we have sort of two streams of efforts here. One is, if you want to denoise EEG, why don't we just use what looks like clean EEG as a baseline reference and use that to denoise bad or motion corrupted EEG? And then the other option was the sensors that I was showing you, like with the glove stream and the camera stream, and we have more people to talk about these later on. So this is going to get a little complicated, so bear with me, I'll try to explain two different methods. The first method we want to use is use motion-free EEG. So this is Matthias playing for about 10 minutes. And you see there's a lot of stuff happening in his EEG. I'm looking at just all the channels together. And then sometimes when he's not playing, he's supposed to be quiet. Well, he's not really quiet, but that was the goal, that if the participant is silent in these few, what I'm calling motion-free segments, we can use these to learn the statistics of the EEG signal when no motion is sort of tapping out your data, and then use that information to clean up all these other segments. And this method is called automatic space reconstruction, but it's fine. Don't confuse that for speech recognition. So once we run this method, this is all of, like I was saying, right? There's a bunch of key presses that happened in this data. You combine all of them in like this averaged oscilloscope trace, and you sort of see, this doesn't look too bad to begin with, right? Because Matthias hasn't been going too crazy. And then when I run this method, I actually ended up losing data. So maybe I'm not running my parameters correctly, so we can ignore this for now. Now go on. So the second method is called DSS, or denoising source separation. Here, the idea is you want to learn a bias, which can be happening. So basically, when you're playing, all those averaged oscilloscope traces I was talking about, that can become a bias. And you can use that bias to run through your entire data stream again, like that 800 seconds of crappy data I was showing you, to sort of extract stuff that is correlated with this averaged bias. The idea being, if Matthias does like some head movements or some key presses, he's not going to be very consistent throughout. So if we extract a bias and use that to clean up, we might be able to get slightly better looking ERPs or evoked responses.
That's ERP.
Yeah, this is an ERP essentially. Yeah. So you can see it's getting slightly better, but again, I wouldn't buy this too much because I think we can tune these parameters much more towards better. And then the final goal was, okay, what if we, so far we were only using EEG data in these two columns, but what if we tried including the glove instead? So think of this as a glove averaged ERP, which is funny that there is some average that survives across all these key presses. And now you use this to bias your correlations, and you reject anything that is, close to the glove stuff. And once you reject those components, what we get out kind of looks comparable to using just the EEG data. So at the end of the day, I feel like there's more optimization to do, but this needs tuning. These two, using the glove or using the EEG statistics, came out looking similar. So we were kind of happy about it.
Yeah, so we've heard about the glove. I just want to quickly introduce what it actually is. So it's a glove for a local project. Yeah, so it has some processor, but the most important thing, an IMU. So it gets the acceleration data in all three directions in the room, like X, Y, Z, but also the twisting, so the angular velocity in all these directions. So these are 6 axes. We're sampling 100 hertz. And yeah, similar is also Timbit. We are streaming the data all the time using this LSL, or the short for lab streaming layer. And with this, we achieve a synchronization to MIDI of, the MIDI and EEG and audio to within 10 milliseconds. And
you have an IMU per figure or just for the?
No, just for the hand.
Just the whole thing, like the sensor eye.
And I mean, here you can see me playing something, and yeah, the video quality is too bad here to really see anything. But basically, you can see the movement data in real time.
Hi, everyone. So as you saw, we need a bias signal to denoise the EEG. So similar to how the glove measures the angular velocity and the linear acceleration of the movement of the entire hand. Another strategy that we thought of using was the DVS cameras. So naturally, the DVS cameras respond to motion in the scene when the lighting conditions are constant. So we use this sensor to first record some synchronized data. The difference here was that we used the LSL layer to just send timestamps at a much sparse rate rather than all the events, because it's producing data at a much higher rate. So here's an example of the stream that Abhinav also showed before that we recorded with the Davis camera. You have the color data, color Davis, so we have the color frames as well as the events. And the signal that we want to extract from the DVS stream is how much the hand moved. So a very basic proxy for that is the event range. So how do we do that? We basically track the centroid of all the events happening within the scene and draw a bounding box around it. So that's a very easy step, and basically just count the number of events occurring within that time. Yeah, and we get a time series signal for denoising.
Yeah, hi everybody. So our idea was to use actually video data to look at different speech production of different sounds. Because during the shaping of the sound, we use a lot like our mouth and our lips to actually shape the sounds. And here we can see like a normal frame video of the sound saw. But then the idea was that with a normal frame camera, we probably lose a lot of the like dynamic, like the temporal dynamics. And so the idea was to use actually also an event-based camera to record this data. And here we have an example. So we see here over time, we see the audio wave, then here just a simple event count. And then here we'll have a frequency plot of the audio. And we can actually see that for the sound so, we get here the consonant and then the vowel. And we can also see here up in the frequency, the different components of the consonant and the vowel. And we can see here for the example so that here the, for example, the onset and offset of the vowel are really small. And this fits also to like most of the production of the S and so is happening inside the mouth. But we're expecting that we probably can also see in the event-based data, some of the lip movements might relate to how the S is shaped. And then the O is, we are opening the lips very small, so we see only very small onsets. Now, if we go to Sa, for example, here we see that the lip opening, you can also just try to say so and Sa, and you will see that
this like number of events. So we're having a way bigger movement is becoming way bigger. We can also see that the frequencies here are different, like in the range of 4,000 hertz, we have a stronger frequency component in the words. So, and then another example would be far, where we can see that we're doing actually the sound in a different way with far. So you can see that the shape here of the consonant and also what we get from the image data is changing. This is like the first, first we're looking at the data a little bit, and we want to do way more like classification and things like this. Yeah, thank you.
Okay, so this project was still part of the noising part. Here I extracted some EEG snippets of a recording I did during some perception experiment. So this is a rather clean EEG recording, but still you can see it as it's a really noisy mixture of activity, which we can model in this way. We can think of it as the sum of electrophysiology of interest. For instance, this was an auditory perception experiment. So the electrophysiology we are interested in is related to auditory response. But there are many other sources of noise. So unrelated physiology, for instance, if the subject was looking at something, we can have visual activity, and we have also physiological artifacts like EMG, like eye blinks, muscle activity, and noise, which can be whatever thing like electrical noise in the room. So, so this was during a perception experiment. So imagine in the case of production experiments where you cannot have such a controlled setting. And when I think about how to denoise this type of signal, I don't know. Can I? It's hard to hear, so you can just point to what you're talking about. Yes. I mean, what I wanted to say that traditional techniques usually. Yeah. Point of the text. The cursor. Okay. Point. Yeah. Usually, people try to filter or do some component analysis, but you don't know if you're actually removing information of interest. You don't know how your ground truth signal is. So maybe you can achieve a really good cleaning of data, but you don't know if you're losing information. And this is particularly true in cases where those components are highly correlated, like in production. So motion-related activity is highly correlated with EMG and with motion artifacts, like electrodes moving from their position. So during the first 2 weeks, oh, it's already, okay. I recorded some data. It was an exploratory thing. I recorded a lot of data, and I mean, it was hard to say, to define a clear filtering strategy. So I started working with Ray on some alternative strategies. So instead of filtering or removing components, the idea is to model the EEG activity we're interested in. Maybe under different conditions using generative models that can capture the underlying structure of the data. And this will be completely unsupervised. So we started some experiment where we just tried to denoise some EEG data on which we had some Gaussian noise. The experiments are still running. I don't have results to show yet. But for the next steps, we would like to condition these diffusion processes with the experimental task or condition. So say to the model, okay, this was an auditory experiment. And hopefully in the latent, I will get a nice separation of the components of interest. I don't know how the denoised signal will look like, but hopefully will correlate with some features I'm looking into in my studies. We can also think of conditioning the model with the waveform itself directly, or some feature we can either learn or extract manually, because we want to see auditory responses to that. So yeah, that's it. Sorry.
So in the vein of using EMG artifacts, we ran a couple of experiments where we had EMG leads attached to the muscle groups that we assumed were producing effects that were going to be in our EEG signal that we didn't want. And so, this is an average of, like 300 media events where someone has moved their arm to an immediate button. And we made the observation that there was a strong negative correlation, particularly in one of the EMGs for this trial. And so using that information and some ideas from automatic noise cancellation, the idea is the top graph is all the EEG channels averaged together. You see there's tons of variance. You can't really get anything out of it. This is the average EMG signal. This big activation here is probably something moving quite large, but it's also very low frequency. And so the thought is, if I take this, correlate it, or rather anti-correlate it with the input signal, it can denoise that signal, get something with much less variance, and hopefully pull out something like ERP. Did this work? I don't really think so. I mean, like, it looks good, but I don't know if in doing the noise cancellation, if I've actually imposed a signal on it. And this is a lot of what Georgia was just talking about. So more experiments with onsets for audio events, and also really trying to disentangle what's what in this to make sure that we've actually extracted the signal. Thank you.
So this project is in the spirit of like understanding whether someone is an expert or a novice at something. So here we're trying to see if we can infer a person listening to a language can actually understand the language, either from the EEG data or from the eye tracking data. So we actually have two languages, English and French. It's a small set of Harry Potter first chapter. So what we have is, first I'm going to show the analysis on the EEG data.
Speak a little bit louder, guys.
Yeah.
And also, please point to the things.
Yeah. So first thing is like, so we have three subjects who are, one person is, the first person is an expert in English, but doesn't understand French. The second one is native English, but also understands a little bit of French. The third person is native French, doesn't understand, is fluent in English. So
I hope so.
Okay. So yeah. So what we're trying to do here is trying to decode the EEG signal from something from the sounds itself. So the first set of analysis is just looking at whether it's the sound signal that is captured or is it something more. So if you can see, there are two bars. The red bar is decoding from the envelope, which is like the energy signal of the sound. And the second bar is the spectrogram. So when you see that the bar, the spectrogram bar is higher, that means the person is able to kind of figure out where the phonetic information is happening. So yeah. So what you can say is people who are native or understand the language well, the spectrogram information can actually be inferred from the EEG data. And the second thing is, so we wanted to see if there is more than just the acoustic information. So we looked at the language in both the languages, so the words, and we kind of extracted some probabilities from a large language model. So we do the same analysis. And again, what we are trying to see here is whether we can infer, they can understand the language. So what we see is when they understand the language, the word surprises actually can be inferred from the EEG data. And finally, the eye tracking data. So for the native speaker, you can see that they're actually focusing on a point. For the non-native speaker, they're kind of dispersed over points. Yeah. So now, you can infer something about comprehension when listening.
Okay, so this is the funnier part. So this was an experiment we did to study this sensory motor loop. So basically, we wanted to see if the EEG tracks steering action and error feedbacks during some video games. So the video game is, you see it on the right side. Basically, you have to keep your mountain bike on track. And from the game, we take out the error you're doing on the track and your steering action. And meanwhile, we record EEG signals, which are synchronized. And later in the analysis, we try to predict the EEG signal from the error and the steering action. So yeah, here is the leaderboard of the demo of yesterday. So yeah, I won. So these are the actual results. So basically, if I try to predict
on the left side, you see here, if I try to predict the EEG with only the steering action, I don't get something significantly better than random. If I try to do it with the steering action plus the error, I get something significant, and that's really nice because it's only data from 3 subjects, and I was not expecting this because there is some motion artifacts and all of that. But yeah, probably it's the signature is really strong. On the right side here, you can see on the left side which channel are best reconstructed with the with the model only with the steering action, and the gain I get by adding the error. So it seems we are mostly improving in central electrodes, but yeah, I'm not that confident in these results because of the data being very noisy and only a few subjects in the data set. And here you can see the impulse responses I get, like those are the model weights of the model I used to predict the EEG signal. And you see the model weights for the steering action, which is, which, I mean, we get a nice impulse response, which nice, it's not that nice. I mean, with only 2 subjects is nice, but it's rather a time bucket 0 when the steering error is has been processed later. So it makes sense. Yeah, that's it.
Hi everyone, I'm Kishan, and this project was trying to understand the neural correlates of motor error. I'm just going to quickly go over our game and the experiment setup. Basically, there was 1 subject, we selected 5 recordings. The first stimuli was a game with no errors. The second part was the introduced errors. Basically, and you can see the car first went left, and then as there's a car incoming, the player is trying to go right, and it doesn't go right, it stays left, so the player quickly scrambles to go right again, and finally they end up right. So, and while they do that, we're recording EEG of their headset and see if we can see something in there. So basically, our hypothesis was we expect a lower beta ERS, event-related synchronization, in trials with errors, even when other possible motor compounds were controlled. So basically, we created this time frequency representation. This is the one with no errors. I would put your attention to around the beta band. 0 is where the event happened. The event being key press, left or right, and the one on the right is where the error, where we introduced error. So they pressed left, the car went right, or they pressed right, the car went left. If you see around the signal on the beta band, which is the 13 to 20 or 13 to 30 hertz frequency range, you see a more suppression of the beta band. This is the key takeaway from this is that as the error goes up, the beta goes down. And so why this happens is there's no well understood theory about this yet, but the most prominent theory is that we all have an internal model of how we represent our events. And as we're trying to predict consequences, and if you screw up with those predictions, something happens in the brain. And so it's consistent with the literature we've seen. And so what's next is we'll try, this was only on 1 subject. I'm going to try to collect more subjects, try to change the parameters a little bit. The car is coming faster. There's 1 car coming and there's another error simultaneously, all these parameters. But yeah, that's about it. Thank you.
Yeah, so here we're using the same game that Shashank designed in a simplified version and trying to take an input directly from our decoding of attention in the brain. So you've probably all heard our somewhat obnoxious stimulus with just 2 superimposed sets of tones that are repeating at 4 hertz and 7 hertz. So when you are able to selectively divert your attention to one or the other, there's a response in your brain that's phase locked to these tones. So we can measure that either with Fourier methods or in this final version that we've implemented just by cross-correlating the EEG signal with the phase frequency match sinusoid. Based on a set of channels that we've selected empirically, seeing from time point to time point whether one is going up and the other is going down, we put an input into the gain where it directs the car in Shashank's game that you just saw to move either to the left lane or the right lane. So this is what it looks like. So he's directing where he's going to send his attention with his finger. You see there's a bit of a time delay, but we are able to successfully eventually move the car over to the other lane.
Yeah, and here this is our performance on our training data, which was collected under conditions where attention was prompted to go to one direction or the other.
Everyone, my name is Karan. So the idea here was working on decoding complex stimuli like people watching movie, which has a mixture of all kinds of modalities in terms of the visual stimuli going on, and the audio, which contains not only speech, but speech, music, and other kinds of sounds. And the idea was to use decode it from this MEG signal. If we could reconstruct any of this audio without putting any constraint on the audio, like it being only speech or music or anything of that. So traditionally this is done using just as the MEG as the input and the envelope of the auditory stimuli, and we try to predict it using just a linear model in this particular case, and we saw that there were not significant differences between the music and the speech prediction from the model. Then we tried to, the other idea, the main idea about this was using neural representations of auditory stimuli to kind of map the MEG to the neural stimuli that we have, which is the code books in this particular case. So this is an autoencoder type model wherein we put in the speech or the audio information, and it converts or compresses it into code books. We have about its compression, but still we have about like 1 million possibilities per frame. And we try to predict it using 2 different kinds of models. One was the linear model and the other was a neural network model. In this particular case, we do see there is a difference between the music and the speech in the linear model that it predicts. So definitely it could either question to the choice of the model that we have in terms of the representation it learns for speech versus music, and or it could be related to the linear limitations of the linear modeling as well. And finally, we have the neural network, which we try to predict, where the random accuracy was 1/1 million, and we got up to 3%. And this is the split of speech versus music that we got. The idea is to explore it further and see what are the neural representations we can use and work on it.
Yeah, so this is another project in audio visual fusion. So what we have is a set of subjects watching a video game, and we have their MEG data. We wanted to see if we can decode the MEG data using basic stimulus attributes, as well as something like salience, which is a behavioral observation that where people are watching something or listening to something without any goal. So I'll just play the video here just to show how the visual salience works here. So the person is just watching the video game and they're moving around, and you can see in the heat map which are the salient objects as compared to the model. So what we did was, so we took the audio and we also extracted something of like a salience from audio, and so we have these set of like envelope as well as like salience features. We wanted to see if we can kind of map from the salience to the MEG. So for this purpose, we use the CCM model, which is it basically rotates all the features so that they're correlated the best. So using the CCM model with different combinations of these features, we see that by adding the like auditory salience, you can improve the performance, and the same with adding the visual salience. But most, there's a big gain coming from the visual salience because you can see there's a lot of visual information coming there. And now we also tested a deep CCM model to see if there are some nonlinear interactions. We did see that there's a tiny gain here, but it's not something that we tested with several repetitions. But this kind of shows us the direction that we can kind of leverage deep learning models and data to kind of find better maps between the salience and the image.
Yeah. So just as a conclusion, we obviously tried very ambitious things. We tackled some new problems and, mixing productions and perceptions and using different strategies. So, I mean, just to conclude, we had a lot of fun. It was very challenging. It was very interesting to interact and to propose all these new ideas, and also to be able to integrate more of the people from the other groups and those neuromorphic sensors. That was really, really interesting and nice. So thanks everyone who participated, and thanks for the co-organizer Munya, Shihab, everyone who was around to help students, Vikash obviously, and all the participants. That was really cool. So thank you.